in a nutshell, we don't have a uniform technology in order to provide services. Even OpenStack, for instance, some services are executed natively just by setting up a Linux container. So the problem that we can see here is that it's difficult to write and deploy new functions on demand because of this kind of heterogeneity. So the idea is, let's start with something that has been proven to work and it is very promising, which is OVN. OVN, for us, addresses the problem of data center-wide orchestration. I'm coming from university, so orchestration is a big word, very nice for us. And apparently, OVN does that job very nicely. Then it runs on different cloud management systems. So we tried mainly with OpenStack, but it works also on the other. But unfortunately, the bottom layer technology, so vSwitch and so on, are the usual suspects. So the idea is, let's replace with those technologies with IOVisor. IOVisor is another name, basically, of eBPF. Already people talked about that. What is interesting to me is that it's fast, is running the kernel, is dynamically injectable at runtime. So you can customize the function, you can compile and inject in the data center. There was a demo showing that. And it is based on a virtual machine that is more flexible than just using OpenFlow actions. IOVisor is basically another name for eBPF. The difference basically is that eBPF is mainly the virtual machine, while IOVisor is a community-driven open source project that includes also other tools like development tools and so on. So it's an ecosystem that is based on eBPF, but is more than that. eBPF is a virtual machine that everybody knows right now part of the Linux kernel. I/O modules are eBPF programs that perform a specific task, like a bridge, a router, and so on. And I/O modules can be combined to create complex services, what we call often service chain. So far everything is known. Hoover is new in this presentation, is a user space daemon that interacts with the Linux kernel and handles the life cycle of the I/O module. So basically the problem is that we would like to inject the code, connect one I/O module to the other dynamically, and so we need a sort of REST server or something similar. In fact, Hoover is a REST server. So I can contact Hoover, I can say, okay, push this I/O module, it takes the I/O module, it injects in the kernel, it connects the I/O module in the proper way, and so on. So it's a high-layer interface that we are using in order to push those modules in the kernel. So let's go to the meat of our presentation. We say that we're using both OVN and I/O modules in this prototype. So let's start with the OVN in order to understand how it works, some internals. And in fact, we're not just presenting OVN, but also the integration of OVN into OpenStack, which is a little bit needed right now, because OVN is basically doing the process from top down. I mean, that's easy to understand. So when OpenStack says create a network, connect a VM to this network, and so on, we can see a flow of information that goes from top OpenStack to the bottom, to the hypervisor. In fact, there is another flow of information that is completely parallel that still starts with OpenStack, but starts with Nova. So Nova goes here and says, OK, I start the virtual machine, and now the virtual machine has a tab, a virtual interface that has to be connected with the network. And this information comes from Nova. So basically, at that point, there's some information that is pushed here by Nova in the hypervisor, and that has to be propagated up to the higher layer in order to complete the chain of the commands. So that's the reason we present also OpenStack here, because OVN alone is not able to create a complex service right now in this setup that we are having, without considering the other interaction that we have thanks to Nova. So the architecture of OVN includes different modules. Briefly, the northbound DB takes commands, high-level commands from Neutron and store those descriptions in a database. The description is very high level, so it says like create a layer 2 network or connect 3 ports to this layer 2 network. The North D daemon here translate those high-level commands into, let's say, flow-like specification that are already specific for each hypervisor. So the high-level command that create a layer 2 network is translated into flow rules, OpenFlow, and something like that are then pushed to OpenFlow controller, sorry, OVN controller that is specific for each hypervisor that in fact pushes those rules into the OVS DB and then go to the data plane. OpenVSwitch, of course, is at the bottom in charge of the data plane. The entire architecture is, allows or requires a bidirectional communication up and down for the reason I already said. So, okay, that's OVN. What about our prototype? Our prototype takes OVN, possibly unchanged or with very little modification. It keeps the OVN control plane while it removes the OVS data plane. So basically, we added this IOVisor OVN daemon that is in sync with all the databases that are already present there. So the northbound DB, the southbound DB, and all the local DB that are on the single hypervisor, the one handled by OVS. So we added this module that is in sync with all the databases, which means that as soon as the database and information in the database changes, IOVisor OVN daemon gets notified, and it can implement the same type of action that has been required, but not with the previous logic based on flow rules and blah, blah, but right now with IO modules. The other component, in fact, is Hoover, which is there in order to accept our request. So it's the REST-based server that is configured with our IO modules. And then, of course, there are IO modules that implement the data plane. The last modification that we did here is basically we start the OVS control plane. So OVS server, OVS DB server is still started in order to be compatible with existing technology. But we turn off the OVS data plane. So only the data plane is deleted. Internals of our prototype. So the main components are the OVN monitor here, which is in fact the component that is in sync with the 3 different databases that we presented above, previously, sorry. We have the main logic, which is the processing logic that reacts to DB changes and implement the same service or the same action according to IOVisor logic. And then this Hoover controller that is basically a wrapper, a single wrapper for all the Hoover that are running in the data center and basically isolates the communication between this central daemon, IOVisor daemon, with all the data, the hypervisor that are around. And then there are some additional modules like Logger, CLI, and so on, which of course are there because we need it, but conceptually those are not so important. So the modification that we did to the OVN framework are very limited. So we disabled the propagation of information of commands from OVN controller to OVS because, of course, OVS data plane is no longer there. We do not start the OVS data plane for the same reason, while for the rest, we kept almost everything unchanged. Also, if there are some information that are no longer used, like the computation of the flow database, the flow rules that should be pushed to the OVS, this is still kept, although is not used in our prototype. So the current status of the project, the the proof of concept that we'll demonstrate now supports OpenStack. So we're in an OpenStack environment that creates a layer 2 network, so very simple service, by the way, on a single compute node. Don't expect us to handle the entire data center right now, through the OVN mechanism driver. So we implemented the changes. We were able to recognize some changes in the OVN database. Obviously, not all the changes that are there are right now understood. So right now we understand when a switch, which means a network, a layer 2 network is created, when a port is created or is detached, when a port security rule is added or modified, and so on. So the layer 2 network is done pretty well with also security rules. Then the code, when appropriate, it inject and configure the layer 2 switch I/O module through Hoover in the single computer server that we have, and it performs the required configuration, like configuring the port security or attaching the VM VNIC to the I/O module. And then also it handles the dynamic mapping of logical names. Because, as I told you before, there are two kinds of information. The one that comes from top, so in this case, a logical name that says connect port 1, 2 to this network that comes from neutron. And then the information that comes from the bottom that says, OK, the actual name of this port, I created this port on the hypervisor, which is called the top 3.4, and then you have to map and understand that top 3.4 is equal to port 1.2. OK, we do that, luckily, so we are able to, in fact, connect the right port to the switch. We created then a minimal I/O modules repository, really minimal. We have one network function right now, which is this layer 2 switch with optional port security based on MAC and IP addresses. And then we created CLI for debugging in order to know and show the status of each I/O modules on the hypervisor and the mapping of OVN information to the I/O modules. So next step in this project, for sure, extend I/O modules in order to support more network functions. So just for starting, router and NAT, which are not supported, so just layer 2 right now. Of course, extend the architecture to handle multiple hypervisor. We already started a little bit, but OK, the prototype has to progress in order to support multiple hypervisor. And since we're coming from the university world, for us it's very important optimization and so on. So when it comes to having the possibility to deploy a network service, a distributed network service across the data center, that's very important to know how to optimize that service, whether to create and where to create those instances of I/O modules. So that's very, very interesting for us. That's left for the future. This project is open source. Everything in our group is open source. So there's the link over there in our GitHub repository. You can try the project, the current status right now, by just launching the vStack. So we modified the vStack script so it can start an entire environment with OpenStack OVN modified by us, Hoover, IOVisor OVN, and all the associated dependencies that are needed in order to make it working. Limitation, of course, it works on a single compute node, and another limitation, it doesn't support yet DHCP. So when the network starts and the virtual machine starts, you have to configure the IP addresses by hand because, OK, we are not supporting that. So time for a demo. I'm good for slides, but not that much for the code. So I leave the floor to Matteo, which is one of the two programmers involved in this.
Okay, so let's start the overview of our demo. So essentially, we have an OpenStack environment with IOVisor OVN as a network backend. We launch, we create a layer 2 network, and we connect 2 virtual machines to this network. Then the virtual machine can ping each other through the switch IO module. But now we change the IP address of the second virtual machine, and then we can see that ping does not longer work because don't match the port security. So we start. Oops. Sorry. Yes. Thank you.
You know, I'm much better at the slides, but he's better with them.
Thank you. So we are starting, we are logging into OpenStack web interface, and now we switch to the networking component and create the layer 2 network. We call it layer 2 net, and we create a layer 2 subnetwork associated to this network. And we set 10.0.0.0/24 as a set of IP addresses, and we create this network. So now we can switch to compute. We want to launch the 2 instances of zeros, and okay, these are the 2 instances. The most important thing now is to connect the 2 instances to our layer 2 network that is actually implemented through IO module. And we can see that OpenStack can now try to launch the 2 instances of virtual machine, and we switch to our console, the IOVisor OVN console. So in IOVisor OVN console, we can see that we are attached to the databases of OVN architecture, and we are also attached to Hoover, that is the daemon that implements the data plane and is able to inject the IO module. What happens now is that the network requests that are inserted into OVN are real-time intercepted by IOVisor OVN and are mapped into the creation of a new IO module. In this case, it's a switch IO module with port security. And also the mapping, the link between the tap interfaces on the hypervisor and the switch IO module is performed automatically, as we can see from this link create. So now let's ask to Hoover what is the current status. We can see that we have the switch IO module that is currently running and just injected into the kernel. We can also have a link, get, that is the list of the links that connects the physical port to the switch IO module. And we can also have the list of 2 tables that are called security IP and security map, that are essentially eBPF maps that maps the number of the port of the switch to the only allowed IP address or MAC address. And this is our way to implement port security. So essentially, the switch perform a lookup in this table and check if the layer 2 MAC or the IP address is the same of this table if it is inserted. Now, what we want to prove is that accessing to the command line to the 2 zeros virtual machine, we want to prove that ping works and actually we will see the debug of the IO module. So we are launching the 2 virtual machine, okay? And the first virtual machine has IP address 10.0.0.4. The second 0.2 instead has IP address 10.0.0.3. And now we ping the second virtual machine from the first one. So, okay, ping works, hopefully. We switch back to the other console. Okay, we can see that the first packet is the ARP request, comes in broadcast, and is forwarded, also the ARP reply. Then we can see a sequence of ICMP request and DCO reply, and this is the output of our IO module that is print of syskernel debug tracing on the trace pipe, essentially. We see this debug of the IO module that now is enabled. We come back to the command line of the virtual machine, and we're trying to configure a different IP address on the second virtual machine, for instance 10.0.0.99. And now we try to ping the second virtual machine, 10.0.0.999. And what we can see now is that the ping no longer works, of course, because we set the security ports. So the first packet, that is the ARP, passes, because at layer 2 the MAC address is correct. But when I have to send back the ICMP echo reply, the packet will be dropped, essentially, because we perform this check on the IP address of the packet, as we described before. I leave the floor to Fulvio again.
So we're now back to the conclusion. So, of course, we have to thank our generous sponsor that we are here because they gave us some money. Some links for the project. As I said, everything is open source, so you can try it. And then questions. I'm done.